For nearly a century, cosmology has rested on a single elegant framework. This standard model maps the expansion of energy from the Big Bang as it cools and structures itself into the cosmic web we see today. It has worked beautifully for decades, explaining observation after observation with remarkable precision. But tucked inside the math was one extremely stubborn number: the Hubble constant. It measures the exact rate at which the universe is expanding right now, at this very moment. And for years, two different methods of calculating it simply refused to agree. One method predicted an expansion rate of 67 kilometers per second. The other returned 73. Most astronomers assumed this gap was a simple measurement error. Cepheid variable stars, the markers we use to calculate distance, tend to live in the dense, dusty disks of galaxies. The theory was that older instruments, like the Hubble Space Telescope, were blending the light of nearby stars together, making them look brighter and closer than they actually were. Clean up that blending, and the numbers would align. Resolving this minor discrepancy was supposed to be the final confirmation of our understanding, tying a neat bow on the history of physics. So astronomers pointed the James Webb Space Telescope at those exact same stars. With a 6.5-meter mirror designed to collect infrared light, Webb can cut through cosmic dust with a sensitivity Hubble never had. It was the ultimate tool built to end the debate. That is not what happened. Webb looked at the stars and confirmed the older numbers almost exactly. The distances held, and the expansion rate stayed right at 73. The most precise observational tools we have ever built are now returning mutually exclusive answers about the fabric of reality. With measurement error confidently rolled out, we are left with the possibility that our equations are missing something vital. Instead of fixing a minor crack, Webb has triggered a crisis. It is proven that our current mathematical map of the universe is incomplete. This diagram shows the contradiction. The first method maps early universe radiation and runs equations forward 14 billion years, predicting an expansion of 67 kilometers per second. The second method measures distances backward from Earth today, landing at an incompatible 73 kilometers per second. In modern astrophysics, a gap of 8 or 9% between two independent methods is not a rounding error. It represents a catastrophic failure of prediction. If the universe is expanding that much faster than our best models allow, then the entire timeline of reality shifts. It potentially makes the universe more than 1 billion years younger than we assumed. This throws every downstream prediction into doubt. It changes when the first stars ignited, how the first heavy elements were forged, and when the chemistry required for life became possible. Webb delivered a second blow almost immediately. It found physical structures in the deep past that appeared long before they were supposed to exist. The standard model predicted small, infant galaxies at those distances. Instead, Webb saw massive, mature systems fully formed just 500 million years after the Big Bang. Building galaxies that heavy, that fast, would require a rate of star formation that our current physics cannot explain. There was an attempt at a correction. Astronomers realized that many of these objects were hosting hungry black holes. The extreme heat from all that infalling gas made these galaxies look much brighter and more massive than they actually were. But even after accounting for the black holes, too many massive spirals remain. These galaxies appear to be converting matter into stars with nearly 100% efficiency, defying every model of galaxy growth we have ever built. The timeline of physical reality appears warped. The universe assembled itself much faster and more structured than our rules allowed for. This animation illustrates the structural discrepancy. Webb found early galaxies stretched into extreme shapes, contradicting core models that expect smooth, spherical halos. This ties into the S8 tension. Astronomers consistently find less matter clustering than expected. The universe is smoother than it should be. Cold dark matter serves as the structural scaffolding for the entire standard model. It dictates where galaxies form and how they cluster across billions of light years. If dark matter particles behave differently than our models assume, the ripples propagate through nearly every prediction in modern cosmology. These are not isolated glitches. The Hubble tension, the impossible galaxies, and the S8 tension are interconnected symptoms of a universe that does not follow our current rules. We should be clear that the standard model isn't entirely wrong. It still perfectly predicts the chemical makeup of the cosmos and the faint afterglow of the Big Bang. Instead, our newest data points refuse to align with the established chart, suggesting the cosmic terrain is broader than we once thought. The math isn't failing, it is revealing a gap where a missing ingredient should be. Cosmology has been here before. In the 1990s, stars appeared to be older than the universe itself. That paradox was only solved by the discovery of dark energy, a force no one had predicted. What currently looks like a fatal flaw in our data is likely the shadow of an undiscovered physical force or a property of spacetime that we haven't imagined yet. A moment of wonder. There is something remarkable about this moment. A species on a small rock is using mirrors and math to argue over a 6% discrepancy in the expansion of reality. The universe itself is not broken. It is doing exactly what it has done for 14 billion years. It is simply our map of the territory that has reached its outer edge. Science has reached the boundary of its current knowledge. As we push into that unknown space, the next version of reality is guaranteed to be stranger and more beautiful than anything we have yet imagined.